All right, so we're wrapping up the continuation or discussion of chemical equilibrium, and we'll get into phase equilibrium today. Just a reminder about chemical equilibrium, we had a generic reaction equation. Is that reversible or irreversible? Reversible. And so we have the equilibrium constant equal to the ratios of mole fractions to powers and pressure and stoichiometric coefficients, as well as, I think this is the more useful form that I like to use, maybe you have used it too, where you're talking about amounts in number of kilomoles for a particular mixture. Often you pick some component and let's say that it's per 1 kilogram or kilomole of that component in that mixture. This K, you can get that equilibrium constant if you know the change in the Gibbs function for that reaction. And these are only for ideal gases. Only for ideal gases. So this, what's that change? There it is. So you have the molar Gibbs at that ambient pressure. So that's that not ambient 1 atm pressure. And often you compute that at 298, but you could compute it at other temperatures as well. You could compute it at some elevated temperature, and then you would get K at some elevated temperature for the reaction. A reminder, what is the Gibbs function? H minus Ts. What's the bar over top of the G indicate? Yeah, it's on a molar basis. Okay. Calculate the change in the Gibbs free energy, or Gibbs function, for the decomposition of carbon dioxide at 298 Kelvin using enthalpy of formation and absolute entropy data, using Gibbs function of formation data, and then calculate the equilibrium constant. So what are we asked to solve? Yeah, that's the change in the Gibbs free energy, or the Gibbs function, and it's going to be computed at 1 atm pressure. That's the knot. So we take a look at our decomposition of CO2. CO2 dissociates to carbon monoxide and 1/2 oxygen. Okay? So what we want is we want to get the stoichiometric coefficient for the carbon monoxide times the molar Gibbs at the carbon monoxide, plus stoichiometric coefficient, the oxygen, G bar O2 naught, minus the new CO2, G bar naught CO2. Did I take this equation and correctly write it for this application? So we can say, well, what is the coefficient? 1. What's the coefficient? 1/2. What's the coefficient? 1. Now, we can get these Gibbs functions using enthalpy of formation and absolute entropy data. I should have written it with the lowercase g bar. Sorry about that. Lowercase g bar naught. Lowercase g bar naught. Lowercase g bar naught. Okay, so how do I calculate g bar naught for any particular component I? Is it h of I bar minus T S bar I naught? So the enthalpy is really not a function of temperature, is it, for true ideal gas? This is all for ideal gases. Is enthalpy a function of pressure for an ideal gas? No. It's only a function of temperature. So we could expand this out. We would say the enthalpy of formation plus some change in the enthalpy from that 298 to whatever temperature it is if we had it at elevated temperature. But for this problem, that it's just, you're just solving it not at 500 Kelvin or 1,000 Kelvin, but just 298 Kelvin. But if you were asked to calculate it at 500 Kelvin, you would not have a delta H of 0. Okay, and then what we have is we have minus T times S bar I naught. So all we have to do is do this for the G bar of the CO. So I have to get the enthalpy of formation for the carbon monoxide minus the 298, which is that temperature, 298 Kelvin, times S bar naught of the carbon monoxide. So we go to our tables for the property. I don't have any sheets in front of me. Okay, I left that sheet at home. So what? So now I can't solve the problem or give you the values. But you go to table A25, enthalpy of formation, carbon monoxide, negative 110, comma 530 minus 298 times the absolute entropy of 197.54. Then you do the same thing for the oxygen, 0 minus 298 times absolute entropy of the oxygen, 205.03. And for the carbon dioxide, you get negative 393, comma 520 minus 298 times absolute entropy 213.69. Okay. You can stick it into there. You'll get a value for delta G bar naught. You can bracket it. Did I solve this problem last time? Why am I solving it again? Really?
Is it recording, sir?
Yeah, it's recording.
Yeah, well, that's the one was recording this time. It wasn't recording last time.
Except for I left my sheet of paper to give me the answer. So if somebody wants to run that one, can you run it for me? 257250.
Yeah, you worked the same problem.
I worked the same problem last time. Skip it. But it didn't record. But you have notes. All right? Well, answer B is going to be very close, but answer B, you use the Gibbs function of formation data that's given in the table, that column right there, and then calculate the equilibrium constant K for part C. It's the exponential, EXP, of negative delta G bar divided by R bar T. True? Done. All I did was use this equation right here to calculate the last part for C, part C, the equilibrium constant K, to calculate the equilibrium constant K. I solved this problem, dissociation of hydrogen, last time, right? I solved it for the AM class and recorded it and posted it out there. We did that one already. Equilibrium flame temperature. So it's a lot like the adiabatic flame temperature. It's not that the chamber in which you're having combustion is less or more insulated. It's still adiabatic. It's just that when you look at the products coming out, they're so hot that it doesn't always stay CO2. Sometimes you get some CO. And it doesn't always stay H2O. Sometimes you get some H2 or some other things. Now, we don't want to throw everything at you, so typically we restrict it to this reaction for dissociation. Okay? Because you could also get some NO, nitrous oxides, out with your fuel. So when you have some dissociation, you can think of it as being incomplete combustion. And then if you go back to the energy equation, you'll get a different temperature. You'll get the equilibrium flame temperature instead of the adiabatic flame temperature. Methane burns with 90% theoretical air to form an equilibrium mixture of CO2, CO, H2O, H2, N2, and it comes out at 1600 Kelvin in 1 atm. Determine the composition of the equilibrium mixture. I believe I solved this in the AM class and I put it up online. Okay? So, in the interest of time, what I'd like to do is solve another problem. This one isn't really asking you to calculate the equilibrium flame temperature. It's just telling you the outlet temperature is, and then you see there's some decomposition. And there will be some carbon monoxide, and there'll be some hydrogen in that mixture.
Is the equilibrium of the mixture in moles? Each one is the same amount of moles?
What you would do is you'd find the right equilibrium reaction equation. That last equation in the appendix is the one that you'll want, the farthest column in this table in appendix. And it's a CO2 plus H2 goes to CO plus H2O. So what you find is you're going to find the number of moles of CO2, the number of moles of H2, the number of moles of CO, the number of moles of H2O. Okay? What you're going to, because you have methane burning with 90% theoretical air, you'll do everything on 1 CH4. 1 CH4. But instead of having as much air as required, look at that, I'm going to solve the whole problem, is you get CO2, H2O, I'm going to put it way over here, N2 with the 3.76. Okay. Now, if I have this just 100% theoretical air, forget about modifying. I'm going to do it in 2 steps. I'll then consider modifying to get 90%. But let's do 100% first. You would have a 1, then you'd have a 2, then you'd have, come back here, you'd have to have a 2 right there, and you'd have a 2 right there. Right? Now let's modify it for 90%. But we're going to do everything. We're going to do everything on 1 kilomole of the fuel. And at the very end, when they want the equilibrium composition, put it in mole fractions. Put it in mole fractions. So what I do here is I put a 0.9. Well, with that 0.9, you have to rethink life in general. Okay. So what we're going to have is we're going to have some, let me scoot this over. It takes a while to develop this type of problem. Okay. What I'm going to have is I'm going to have a new player. It's going to be CO and another player, H2. Do I have any O2 going out with the products? I look in the problem statement. Is there any O2 listed? No. Is there any NO listed? Because they don't list it, it's not coming out with the products. In reality, you may have another reaction going on as well as this one and as well as that one, and it gets, life is very complicated. Okay, so all I have are these players here. Now what I have to do is I have to go back and scratch my head, and I have to say, you know, I'm going to probably get an equation where K is equal to the number of moles of CO raised to the 1 power, number of moles of H2O raised to the 1 power, the number of moles of CO2 raised to the 1 power, and the number of moles of H2 raised to the 1 power. And when I go over here with that P over N total, that whole thing, because the exponent 0, it's just 1. So the pressure doesn't come into play. Okay. So I look here and I think, you know, my strategy's typically been, instead of getting 4 equations, 4 unknowns, or I'll get 4 equations, 4 unknowns, but I'll reduce it to 1 equation with 1 unknown. So what I'll do is I'll pick the final amount of the number of carbon monoxide in the final mixture as my Z, and then that'll be my one unknown that I bury everything into. And so right here is this looks now like Z, but I have to express the number of moles of H2O, number of moles of CO2, the number of moles of H2, all in terms of Z. How do I do that? Well, I do 3 balances. What's the first balance? Carbon balance. So let's go ahead and write a carbon balance. And let me do this. I'm going to leave a symbol A, symbol B, symbol Z, and a symbol D. It just helps with the algebra. Okay? So for the carbon balance, how many carbons do I have on the left-hand side? 1. How many carbons do I have on the right-hand side? Well, for every CO2, I'll have 1. And for every CO, I'll have 1. Aha! So this being A being the number of moles of CO2 in equilibrium mixture, that's equal to 1 minus Z. True or false? True. Guess what we substitute right here? 1 minus Z. Keep working. The next balance, you could go hydrogen. Hold it, we don't have, yeah, we do have hydrogen. Or we could do oxygen. I think the oxygen is the next best one to do because, you get this and you substitute and eliminate. Let's do the oxygen next. How many oxygen are over on the left-hand side? Okay, it's 90, it's 4 times 0.9. 3.6, true, 3.6. Everybody follow that? 3.6, very good. Now I look and I say, okay, for every CO2, I'll have 2. If you're really good, you'll say, I know how many CO2s I have. I have 1 minus Z. Fine. But don't make errors in this steps, okay? Maybe you just want to leave it as A, but you already know what A is A is 1 minus Z. All right. I look at it. How many, for every H2O, how many O do I have? 1. And for every CO, that's a Z, how many O's do I have? 1. All right. So now at this point, I go ahead and do some algebra, but I make sure and not make an error because it's so error prone, at least for me. So I have to then solve for B. Man, I can't do this. I got to go slow because I know it's so error prone. So it's 3.6 minus 2 plus 2Z minus Z is equal to B. 1.6 minus Z. And that's exactly right. So we put that for the H2O because that's what is right here. 1.6 minus Z. Now, the last balance, and I didn't leave enough room. Can I erase this and try and squeeze it in? Is our H balance, hydrogen balance. How many hydrogens do we have on the left-hand side? 4. And so for every B, I have 2. And for every D, I have 2. And the B, we already solved for that. That's 1.6 minus Z. So 4 minus 2 times 1.6 plus 2. Actually, do this. Get rid of that 2. Get rid of that 2, 2. So there's too many 2's. So 2 minus 1.6 plus Z is equal to D. So D is Z minus 0.4. Look at that and tell me if I made a mistake or if you agree. Plus 0.4. I don't trust myself, see? I have to go to the experts. Help me out here. Is it Z plus 0.4 or not? Yeah. And then at this point, I would just solve, I would look up at 1600 for that reaction, I would find, oh, that's 10 to the, let me look at what it is. Got to find that reaction. It's 1600, 0.474. And then I have one equation with one unknown. I solve for the z's. You have to do it on your calculator. How many people can solve that problem on their calculator today? If you want to go and turn this into mole fractions, you'll have to consider the amount of N2, which doesn't participate in that reaction, if you want to turn it into mole fractions of the outgoing product gas, because N2 is part of the outgoing product gas, okay? Yeah. I want to spend some time on this problem. We have carbon monoxide enters a well-insulated reactor and reacts with 100% theoretical air at this temperature. An equilibrium mixture of CO2, CO, O2, and N2 exits the reactor at a pressure of 1 atm. So the pressure doesn't change, but it's going to come out toasty hot. It's combustion. For steady-state operation, negligible effects of kinetic potential energy. Determine the composition and the temperature of the exiting air mixture. This is one of these cases where you cannot solve for part A first and then for B. You got to solve for both of them together because the chemical equilibrium equation requires temperature to get the K, the equilibrium constant. And the energy balance is what allows you to get the K. But to get the energy balance to give you the K, you have to know the outgoing distribution of the products. And some of the carbon monoxide is in the product stream. Not all of it combusts. Why? Because it's in chemical equilibrium. So what's the chemical equilibrium equation? CO2 plus, goes to, I got to get it right. Plus 1/2 O2 goes to CO2. Think about our carbon monoxide is our fuel. And we're combusting it to go to all the CO2. So this is our combustion equation for our energy balance. But we also have a dissociation equation. CO2. This is the way it would normally go. It would be complete combustion. It'd go like this. But we have a dissociation equation, which is that this is CO plus 1/2 O2. You want to write it the way that it's found in table A27. Is that the way it's written in table A27? Yes. I know this is a symbol saying it's decomposing, it's reversible decomposition, but here we have this combustion. That combustion says it goes completely to carbon dioxide, but it doesn't. So we're still bringing in 100% theoretical air, true? In reality, we get a lot of carbon dioxide out. We get some carbon monoxide out. And because we got some carbon monoxide out, we're going to have some unused O2 out as well. One thing I left out is where do we get the oxygen from? So I left out the 3.76 N2. So that goes to CO2 plus 1/2 3.76 N2. Okay, so then we still have the 1/2 3.76 N2 going out, right? Do you understand my little fix there? Okay, so I even set it up where I'm going to be solving for this Z. If I knew the temperature, I could get Z directly, but I don't know the temperature, so what I'll have to do is iterate, because the temperature is going to come from an energy balance. Okay, so let's take a look at our equation that we're most familiar with, our equilibrium equation. K, which is a function of temperature, I'm just emphasizing that, don't forget it, is equal to, we're going to have the amount of CO raised to the 1 power the amount of O2 raised to the 1/2 power divided by the amount of CO2 raised to the 1 power. We'll have the pressure over 1 atm. It's 1 atm pressure, so it's 1 over 1. And then we're going to have the total number of moles, which is going to be the amount of CO2 plus the amount of CO plus the amount of O2 plus the amount of N2. Don't forget the N2. All raised to the power 1 plus 1/2 minus 1, which is just raised to the power 1/2. Did I go too fast or you follow it? I already substituted the z because z I usually like to have that. Otherwise I got multiple equations, multiple unknowns. I do a carbon balance. I get an equation. So I'm going to have 1 equal to A plus Z. I've seen that before, haven't I? A is the amount of CO2. So this goes to 1 minus Z. From the carbon balance, I come down here, 1 minus Z. It starts to simplify a little bit, but don't get too excited. These things are never all that simple. Right? All right. The next balance equation, let's do a oxygen balance. Okay, oxygen balance. How many do I have coming in on the left-hand side? Go slow here. You can make a mistake. You can very easily make a mistake. It's 1 or 2?
2.
It's 2. Man, you are so smart. It took me half an hour. It took me half a day. It took me half a week to figure out a mistake like that. Why is it not 1? Professor, 1/2 times 2 is 1. They forgot the O with the CO. Yep, exactly right. So it's 2 is equal to, and then you're going to have A times 2, and then you're going to have Z times 1, and then you're going to have B times 2. Did I get everything on the other side? We'll substitute for what A is. A is 1 minus Z. And then solve for B. You solve for B. Do it. Go ahead. You solve for B. I'm tired of doing algebra. All right, we got one answer, 0. B is equal to 0 or 1 minus what? Z? Or minus Z? Half a Z? We'll do it the old-fashioned way. I used to do it this way. All those that think it's Z over 2. All right. All those that think it's 0. That one kind of went for a while and then it faded. Right. 1 minus Z and negative Z. So it's Z over 2. Very good. So B is Z over 2. Then we come up here and we have Z over 2 to the 1/2. And then this is Z over 2. What about the number of moles of N2? This, I think, is 1.88. Is 1.88 times 2, 3.76?
Yes.
Now, this is all where you have on this side of the equation everything in terms of Z, but over here is T, T, T. I have to go do the energy balance. Q dot divided by N dot F, but you said it was adiabatic. W dot divided by N dot F, there's no shaft work, it's just a reactor. 0. So we have the sum of the stoichiometric coefficients times, however you want to write it, but we could write enthalpy of formation plus the change in H bars, all for the products, minus the sum of stoichiometric coefficient. I'm running out of room again. All our reactants come in at the 298. So that's easy, all those delta H's. And only one reactant comes in with the non-zero enthalpy of formation. So it's the enthalpy of formation of the CO that's only our fuel. All right. Then we have the enthalpy of formation of our products. Well, we're going to have to deal with carbon dioxide, carbon monoxide. Oxygen has a 0 enthalpy of formation. Nitrogen has 0 enthalpy of formation. But those delta H's, it comes out some unknown toasty hot. So you have two equations, and there's really not much more simplification you can do. You just have to go and start iterating. Pick a temperature. Once you pick a temperature, get the Z's. Come over to the energy balance. Now you know what the coefficients are. You can see if you solve the energy balance equation. You're not. Change the temperature. Once you change the temperature, you go back and forth, okay? Let me do this. I solved it in Excel, so I'll just show you the Excel. So carbon monoxide, adiabatic flame temperature. I wasn't content. First of all, I do this line with 100% theoretical error, and I make sure it's balanced. Then I'll come in with another line, which is I change the percent error. Here I changed it to 150%. So I know that we have 100%, but I changed it to 150%. I can change it back. Right over here, the solution to 100%, okay? So I solved it 150%, 90. Okay, so if I have all that, then I have this nitrogen, more nitrogen, and I have this amount, but I don't know the distribution. So down here, I have color-coded Z, which is my number of moles of CO. And if I look up here, I just say, what is this? Guess what? It depends on the number of moles of CO, which there's a few loops here, but this one is just copied up from there. So if this is the key, if I change that cell right there to be 0.29, okay, it's going to come up here and change these others. Watch the cells right here, okay? They're going to change, okay? How about 0.27? They change. And then I don't know the outlet temperature, 2200. Fine. Well, I have to do all of my energy balance to find out what the Q is. Well, the Q isn't 0. It's not 0. And the the chemical equilibrium equation, that's not satisfied either. So what I have is I have a combined error, which says the absolute value of cell C4 for the chemical equilibrium, and the absolute value of C22, which is for the energy balance. And I want both of those to go to 0. Well, once you set it up in Excel to get it to percolate, you say, I go up to data, I go over to solver. How many people have ever seen solver? Solver right here. So it says, take that cell C25, that's right down here, minimize it. I don't think I'm going to get it to perfectly 0, but get it small, get it down to 0. Start root finding, take it to 0. By changing, and then it comes up here and it's going to change 2 cells, not just 1 cell. That's why you need solver. You hit solve, and then this is the point where you say, I hope it works. But if you have it set up, it usually works. Because it's nonlinear, if you give a really bad guess, it can march off in a wrong direction. So there it is. There's the answer. It's 2090 degrees and 0.0106. Okay, so what did I solve this for? Was this 150%? So over here is 150%. Oh, it's what I had obtained earlier. But if I really only want 100%, then I have to hit solver again, do solver again. It remembers which cells you had, and then it solves it. So for 100%, it comes right in at 400 Kelvin, 2399, and Z of 0.125. So that's how many moles of carbon monoxide you get out for every mole of carbon monoxide that went in as the fuel. Everything's done on 1 kilomole of the fuel. Are we out of class time? No. Who's packing up? Hey, Thomas, why are you packing up? All right. So now let's go back to this, since I have 7 minutes left. Phase equilibrium. Well, we've already had problems where you have liquid in equilibrium with the vapor. Two phases in equilibrium. True or false?
True.
Yeah, it was true. Do you know that now we can go back and revisit that problem and we can find that it's the chemical potential of the liquid that's equal to the chemical potential of the vapor. And the chemical potential is the molar Gibbs of the liquid and the molar Gibbs of the vapor. Now the textbook likes to put like this mark and this mark for the liquid and the vapor. 1 prime, that's not one derivative, and 2 prime, that's just saying this is liquid, this is vapor, different phases. Because now that we have the notion of chemical species, you could have component A and B in the liquid, and component A and B in the vapor. Two-phase equilibrium. A good example would be I have a two-phase mixture of water and ammonia, NH3. Remember when we talked about the absorption refrigeration system? We said cold water likes to gobble up or absorb the ammonia. Hot water likes to kick it out. Well, you start changing the temperature and it starts changing then the relative proportion at which ammonia likes to be dissolved in the water. It kicks it out at high temperature. But it goes back to saying that the chemical potential of the water is equal to the chemical potential of the water, this is a bar right up there, H2O, in both phases. And likewise, the chemical potential of the ammonia, NH3, is equal to the chemical potential of the ammonia. So there you go. So you can now at least talk to some chemical engineers about phase equilibrium and the criteria for such. Let's solve a problem. Use property data from the steam tables to show the specific Gibbs functions of saturated liquid and saturated vapor are equal for steam at 150 degrees. So, okay, this is that Gibbs. Let's not do it on a molar basis. We can do it also on a mass basis. Because our steam tables are on a mass basis, and we're going to calculate it for G sub F. What is G sub F? Saturated liquid. And then we're going to cut G sub G. What's that? Saturated vapor. So we're going to have, I forgot, what is the definition of G? Is it H minus TS? Yeah. So we'll just get H of F out of the steam tables at 150. We'll take and make that temperature, make it Kelvin. This is one of those cases where if you add that 0.15, you'll actually get it to agree to 3 digits, but not 4. Okay, but if you don't add the 1.5, it really will disagree on that third digit. Okay, then you multiply by the S of F. Likewise, H of G minus 150 plus 273.15 times S of G. You compute both of these, just getting the values out of the tables, and what's surprising is how good they agree. And so it basically confirms 147 kilojoules per kilogram, 147 kilojoules per kilogram. Don't go trying to get the fourth digit to agree, significant digit, okay? So now that didn't check it for 2 species in there. That's just a single species. I got 3 minutes. 3 minutes, Thomas. You're good? Now recall the state principle. Chapter 2, right? So it said that I need so many independent intensive properties to fix the state. Well, now we generalize, and it's called Gibbs phase rule. This is the number of independent intensive thermodynamic properties needed to fix the state. This is the number of components. You could have one component, sure, you'll just get back to the state principle. But now you could have 2 components, water and ammonia, and the number of phases. Did I derive this equation? No, I just give it to you. Do you have it memorized? Let's apply it. How many independent intensive properties F, that's what they're asking you to solve for, are required to calculate the specific enthalpy of pure water in liquid phase? Well, I only have one phase, and I only have pure water. So I go F is equal to 2 plus N minus P. This is 1 minus 1. They cancel. I'm back to what I anticipate. So if I needed to know the enthalpy, maybe I would have to specify temperature and pressure. It would work. How many independent intensive properties are required to calculate the specific enthalpy of a liquid solution of water and ammonia? N equal to 2, liquid, P is equal to 1, F is equal to 2 minus, plus N minus P, 3. So if I wanted to know it, I'd have to specify maybe the temperature, maybe the pressure, and maybe the mole fraction of NH3 in the solution. See how that goes? Last one. How many independent intensive properties F exist for a pure substance in an equilibrium mixture with solid, liquid, and vapor phases? P is equal to 3, present. Well, it's a pure substance, N equal to 1. So F is equal to 2 plus 1 minus 3. What does that mean? That means really you're talking about the triple point. Temperature is not independent, pressure is not independent, specific volume is not, it's just triple point, okay? So there you go. Thank you very much for your attention.